All right, good afternoon, everyone. Welcome to my talk about C# language internals. I'm Bart. I work at Microsoft back in the States. I'm currently on the Bing team working on high-scale services for event processing systems, and I'll talk about that tomorrow in my talk about high-performance .NET code. Today, we're just going to take a look behind the scenes of your favorite C# language features. It's actually part of some series that I've been doing for the last maybe 3 years or so, 2-3 years. At various conferences, I've given this kind of presentation. Now, the nice thing about it is that the content is always different. There's enough language features to talk about. So if you want to see some more content on this, you can actually go to 2 places. You can go to channel9.msdn.com, which is the video website at MSDN. There you can find plenty of videos from different conferences in the Netherlands, in Belgium, and some other places where I've given a similar talk. And there's also a 2-part Pluralsight course on C# language internals, which is kind of the same content, but of course, there we have much more time to go into much more depth. So that's just to set the scene over here. Now, the way that this talk actually works is very simple. I don't know what's going to come up next. I'm just going to ask you what you want to see. It's divided into 3 pieces. I have some starters, which are just to warm up. Then we have some main courses, which are a little bit heavier, and then some light desserts to sort of stop with. The mechanism is quite simple. We pick something, depending on what you pick, we'll pick our utility to study that language feature in much detail. We may actually go into IL code to see how it works, so fasten your seatbelts. We may open WinDbg to see like the native generated code for the language feature. Or we may actually open the Roslyn source code, the source code of the compiler, and actually attach a debugger to the compiler to step through some of the compilation process, or sort of point out some interesting tidbits as we browse the code. So let's get started by, well, what else to start with than a starter? So we could talk a little bit about array initializers. Very simple language feature, seemingly, but has some interesting code gen. We could talk a little bit about events, which has some interesting stuff to do with synchronization. That's all the way back to C# 1.0. We can also go a little bit more modern with interpolated strings, which were introduced in C# 7 very recently. And they also have some interesting code generation. So maybe a show of hands. How many want to see some array stuff? OK. I'll have to assess how much that is. How many want to see events? Well, it's a little bit more, I think. And interpolated strings? My lord, I think the events will have it, actually. Yeah. OK, so we'll do events for now. OK, so I'll talk about very simple events, actually. So let me actually just open some piece of code here I have sitting handy. So that's the simplest piece of code you could have. Actually, it's not the simplest. We don't need the using. Oh, we do need the using. Sorry, we need the using for the action over there. But so very simple event over here, public event action A. Could make it simpler if I don't do static void main, but whatever. So that's the simplest kind of event you can have. But there's some interesting tidbits behind this. Like events actually are based on delegates. So one thing, of course, that everyone likely knows is it doesn't matter it's an event handler of T or some other delegate type. Like I can use the action delegate type here. It just works fine. The language doesn't care what delegate type you use there. But there's some interesting stuff that needs to happen behind the scenes to make this actually work. Because first of all, if you have events, well, you can declare them in 2 different ways, right? Like I guess many people know that you can also take control over the way that event handlers are added and the way event handlers are removed by adding an add and remove clause over here and actually writing your own code using the value, which is the thing that comes into the plus equals or minus equals operation. So you could do that. And actually, there are many frameworks that do that, like, for example, Windows Forms, because if you use the default syntax, which I had on the screen just a moment ago, and I'll revert to that right now, if you use this syntax, you end up with a field behind the scenes which holds the delegate instance that you will use to do the invocation of whoever is attached to that event. And so if you want to avoid the cost of those fields, you can actually use add and remove yourself and build an event manager. And in fact, if you browse the source code of Windows Forms, you will actually find an event manager that actually does all the registrations of events behind the scenes and not relying on any fields. But I'm going to focus on this particular guy here. Now, what's interesting about this is that when at some point I do say, for example, a plus equals, and then I should make it static if I want to make this compile eventually. If I do a plus equals the simplest possible, lambda over here, for example, something interesting has to happen. The way that those delegates get combined is, of course, using the same thing that's used to do a combination of two delegates. So like if I have action A over here, and I have action B equals something else, these are two different, bodies here, I can do action C equals A plus B. Right, you can actually add two delegates together, and then you end up with a multicast delegate. And so this multicast delegate, the way that this A plus B actually translates is as follows. It simply does delegate.combine of A comma B, and then it will cast the result over here to action and assign that to C. So when an event starts out with no event handlers attached, it starts off as null. And then later, when you do plus equals, it basically does a combine inside the add method to add those two things together. But there's, of course, a little caveat there. What's the caveat? That you may actually have concurrent accesses to the event plus, plus equals and minus equals to add and remove event handlers. So there can be some concurrency there, and you could actually be losing things because this plus is not atomic. As you can see over here, if you would do A plus equals something, let me do instead of this, let me do A plus equals B, then you end up with code that looks like this, which is pretty much the same as in multi-threaded code writing something like A plus equals, 3 or something, where of course the read from A and the write to A is not atomic. So we have to do something in order to make this an atomic operation. And so the way that this works is by using some interesting code behind the scenes. So I'm just going to remove all of this. And let me actually compile this over here using the C# compiler. I'll do /o+ to do it in an optimized build. It says that the event A is never used. I know that. It's just for demo purposes. But we'll actually use ILDASM over here to have a quick peek at what's going on behind the scenes here. And so you see that we actually have our event here. For some reason, events are rendered using an upside-down triangle. We sort of have all the shapes in ILDASM, like it doesn't have any meaning. But then, if you take a look over here, you see this add and remove handler. They have been generated for us. And you see the add A and remove A. If you go in here, you can see this beautiful thing over here, interlocked compare exchange. Typical way of doing, concurrent programming is to do read a field, then you try to update the field, provided that the field hasn't changed from the original value that you read before. So this thing has actually generated a while loop that, infinitely long, will sort of try to swap in, the thing that you're trying to add in a concurrency-safe manner. In fact, in older versions of the compiler, we used to have synchronized access here, just like you have in Java, a method implementation attribute saying this thing needs to be synchronized, which took a lock on the current instance of the object or on the type in case it's a static event. And that's not a good thing. So I believe it's starting from C# 2.0 or something. This has actually changed into using interlocked compare exchange. So now let's actually take a look at the source code on how this thing actually is implemented, because that's one of the beautiful things you can do nowadays. Literally a couple of hours ago, I did a git clone of the Roslyn source code. How many of you have actually been to the Roslyn GitHub page? Yeah. Did you look in the code a little bit? Yeah? OK. So I just did a git clone this morning. So it's actually the latest and greatest version of the compiler I have sitting here. And so I've opened a solution called compilers.sln. I've opened a whole bunch of things here. But in fact, if you want to boil it down to the essence, it's quite easy to unload pretty much everything. This starts off with, I believe, 56 projects or something. And if you open roslyn.sln, it's like 150 projects. Like you don't want to open that whole thing and hit F5 every time you want to try to do something. So just open compilers.sln, and then just unload everything that's test code, and you end up with 8 projects which are the core of Roslyn, the C# compiler, for example, over here, the command line compiler, and those kind of things. And so what I've done is I've set csc.exe over here as the startup project, and I've passed in over here, I'll just read it out loud, the command line to compile a file called demo.cs, which sits on my desktop, okay? So this demo.cs file, which we're using for our demos over here, will get compiled as soon as I hit F5. So let me just do Control F5. It's a different file than the events.cs that I'm showing you right now. We'll go into the events stuff in just a moment. But I'm just hitting Control F5 and it's running, and you will see a version of the C# compiler, version 42. It's not that we've been very busy the last couple of nights and we sort of shipped, C# 8 all the way to 41 without you noticing. It's just when you do a local build, you end up with version 42. It says developer build over there. And so I'm actually using some new feature just to prove to you that this is actually C# not 7, but 7.1 already from the master branch, where we have support for a feature called async main, which is not enabled yet, but I will actually just go into the code to show you how this actually works. I have this little piece of code here sitting behind the scenes. That's the one that I'm compiling by attaching the debugger to the C# compiler. And you see over here async task main. This is a new thing that will come in C# 7.1. You can actually have async methods for the main method. Instead of having to have synchronous methods that return void or int, you can also have async methods that return task or task of int. And so that's the piece of code I'm actually going to compile. I'll also add my event over here so we can study that in a little bit more detail. So I'll just have my event action E here, the same as the one I had in the other file. And so I'm just going to step through the compiler now to sort of give you a sense for the way you can sort of study those language features at your own pace at a later point in time. So for async main, I've already set some bookmark over here just to make it a little easier to navigate today. But so the way that async main is actually built is by generating a synthetic entry point. A synthetic entry point that's actually a synchronous method, because the CLR only supports synchronous entry points. And all that entry point will actually do is it will generate a forwarder to your asynchronous method underneath, which will actually call getAwaiter.getResult on the task returned from the main method. Okay? So it's as if you're writing this little bit of plumbing yourself. The reason for using getAwaiter.getResult is because it unwraps exceptions. Unlike, for example, getting a task and then simply doing return task.result, where you will get aggregate exception as opposed to the original exception. So it generates the code using getAwaiter.getResult. And this works against anything. It doesn't even have to be a task. It can be anything that's task-like. So anything that supports, the getAwaiter and getResult pattern will actually work with this. Okay. So I'm just gonna, hit F5 now over here to now build, my little demo.cs, and we'll step through a little bit of the source code. Actually, I have some breakpoints that I set up a moment ago. But you see the C# compiler is spinning up over here. And the first thing that's interesting to know when you're actually going to explore the new language features is go to this particular file here, messageid.cs. You don't have to remember that. Just search for literally C# 7.1 across all of the text files. And there you see feature detection, because the C# compiler can actually be used to down level. You can actually compile C# 6 and 5 and 4 by specifying a certain flag, the /lang version flag. And so this is a new feature in C# 7.1, but I'm actually running the compiler with default flags, which means it will still think that C# 7 is the latest, because everything higher is kind of experimental. And here you can already start to see the menu of new things that are coming in C# 7.1. You see async main, the default literal. The default literal is actually this. I can write int x equals default without doing default of int. That's using target typing. So if you want to assign it to an int, it will automatically infer that you mean to write default of int over here. So that's another feature. But so this is the feature detection stuff, and that's the one that was responsible to give this error message on the screen earlier saying async main is not yet available. So let me just step through this a little bit more. Let's do a little bit of hacking here. You see it's actually calling some helper method over here to ask whether a feature is enabled. And so where are we coming from? We're actually coming here from some piece of code that's trying to find the entry point by using a set of candidates. And in fact, if you take a look at the source code here of the C# compiler, you will actually see that it's using its own dog food all over the place. For example, what you have over here, if I go a little bit higher, is a local method, local function. That was actually shipped in C#7, and the compiler uses that already. You also see here an array builder of tuple types, also a new C# 7.0 feature. So it's full of all the new stuff immediately being used inside the compiler source code. And so what's happening here is that this piece of code is actually going through all the candidates to try to find a synchronous main entry point, and now it's also trying to find an asynchronous main entry point. And it has found one, but it's now checking whether it should allow you to use async main, because that's a new C# 7.1 feature. And so it's going to complain because it's still configured to use C# 7. But of course, no problem here. What I can do is I can just say that the available version is the required version in the debugger to just bypass this check, right? So let's just do a little bit of hacking here. I'm just going to pretend I'm running C# 7.1, and now the feature will just continue compiling. So if I now hit F5, you see it actually compiled the whole thing fine. And I'm actually ending up here in another breakpoint that I've set, which is the async forwarder that I was pointing out a little bit ago. And so if you just search, and the simplest way to actually search for this kind of stuff is as follows. You find a new feature, you see the place where you see the first hint for that new feature in the source code, and then the very next thing you do is you click over here on the GitHub source code. And then you just double-click on the change list, and lo and behold, there it goes. That's the check-in of the compiler team to add this feature to C# 7.1. So now you can start to find all the affected files where you end up having any changes related to this new language feature. But so what you see over here is that the body of this synchronous main method that we're generating is effectively just containing a call to get the waiter get result with a little bit of decoration around it, such as a return statement and just a block, curly brace, close curly brace, and then inside of it, it will just do get a waiter get result for you, and then just return to the caller. In case it's async task of int, it will do pretty much the same thing. It will just return the result of get result, which will contain the exit code, right? So now you can start stepping through all of this. And if you like, I could just stand here and just do F10 for likely the next 6 hours, to just do line by line to see the IL code being written. We're not going to do that. I don't want to bore you to death. But I'll just show you one more thing, which is the place where that event stuff was actually happening. Actually, I didn't have to exit the debugger for that, but fine. The event stuff is sitting over here. And the thing I wanted to point out by just going to this event stuff, because it's kind of a trivial language feature, but still, not everyone knows that it's actually using some synchronization stuff under the hood. If you actually start browsing the compiler source code, you end up with a lot of references to the language specification and also a lot of historical notes, like, this used to be this way in, Visual Studio 2013, and we changed it because of that, and so forth. Here's a little bit of information which is likely easier to read than what we saw in ILDASM. Like that compare exchange, well, you can spot that, but it's not that easy to spot the fact that there is some do loop around that whole language construct. So you see over here, this is the code that this tries to generate. And so now you can start matching those things up a little bit. So you see what's really happening with events is that we read the backing field. But of course, by the time we read the backing field, immediately after that, somebody else could be winning the race over here for checking in another event handler, either by doing plus equals or minus equals. So we have now to guard against doing an invalid assignment where we override a change that somebody else has made in the meantime. And so that's what this code is doing that I was sort of pointing at a little bit ago. But you see over here, we try to do the combine, cast it back to the original delegate type, and then try to do a compare exchange, which is a conditional assignment based on an old value that we read. In case that's actually going through, we can just bail out from that loop, and everything is good. If that doesn't work, then we'll just retry rereading that field and sort of continue doing that. And so what you see here is actually something that's very common to the C# compiler. there's a lot of complexity, of course, but in a lot of cases, new language features just translate to old language features. If you look at that async main, with just a couple of files touched to just make some forwarder that makes an async main be called from a synchronous main, because that's all the CLR knows about. So it's just going to rewrite it as if it were a human being writing the code that would do that trivial piece of code as well. In fact, over here, we could have said in C# 1.0, well, we will not provide you the convenience of field-backed events. You just have to write this code yourself. And in fact, the compiler is doing that. Compiler is pretending there exists a version of C# that does not have this language feature. Let me translate it into something simpler. And in fact, all of those rewrite steps sit in a folder called lowering. So if you go and look over here, you will find a folder deep down here called lowering. And you see a whole bunch of language features here, such as async methods. These are all based on lowering. For each, for example, is based on lowering. Like some subset of C# doesn't know about a for each loop, it only knows about while loops. So we can just compile things into a simpler set of primitives. So once you get your hands dirty with this, this code doesn't look as complicated as you may think at first, because all this is doing is just generating, code that accesses fields, that has while loops inside of it. You can actually find over here this whole loop construct will sit in here somewhere as well. Now there's one more thing. You see over here that we also use this thing called getWellKnownMember. This is also a beautiful place for you to go and take a look at the things that the C# compiler knows about. These are features inside the .NET framework that the compiler can talk to. For example, for events, it needs interlocked exchange. For other things, like string interpolation, it will need string.format, for example. So you will find all those members over here. But you will also be surprised that in a lot of places, we actually have checks that see if this member is available. Because on certain frameworks, we may not have interlocked compare exchange available, and we need to do some other strategy instead. And so you see over here, if we don't have this, we'll actually go down this other code path over here, where we will actually generate alternative code and make the method synchronized, as opposed to using a while loop ourselves. So there's a lot of forking in the code to sort of support older framework versions where certain members may not be available. Okay? Good. So that was kind of a little warm-up. We went through the debugger a little bit, see how things kind of work, and sort of looked at a pretty simple, relatively simple language feature. Okay? Now let's go for the main courses. I have 3 on offer tonight. One is display classes. Display classes are used by lambdas and anonymous methods, and now also by local functions in C# 7.0. Quite interesting new language feature. Switch statements have also grown a lot over the years. Like now in C# 7, we have pattern matching support, and we also have async methods over here, which got a little bit of a revamp in C# 6, because now you can await inside catch and finally blocks. So I think they're all very appetizing, but let's just do a little vote here. How many want to see display classes? Okay. How many want to see switch statements? Okay. How many want to see async methods? That's what I feared. Okay. Okay. I've had this on the main courses all the time, and I had to throw out rotten switch statements and things from my fridge for display classes because they never get eaten. So we'll just do async methods instead. Okay. Async methods, well, you already know where to look because I mentioned it just a moment ago. Async methods are based on lowering. So what that means is that async methods are just one big piece of deception, right? Like, it's as if you're building a state machine completely yourself. That splits up the method and does all of the tracking on your behalf. But of course, now that you have the C# source code available, you can now start seeing how all of this voodoo actually works, okay? So let's take a look at where this voodoo takes place. It's pretty much all over here in the async rewriter. Contains like 6 or 7 files or a little bit more, not too bad. But let me just start by writing a little piece of code at the command line and sort of looking at the base functionality in an async method, and then sort of work our way up from there, okay? So let me just do async.cs over here. Is this actually big enough for the back, or should I boost it? Boost it, okay. I'll boost it. 36. Good? Good. OK. Static void main, just to be happy. Could use static async main, actually, but let's not do that. OK. Static async task of foo async. I think that's the simplest async method you can get, right? Like, an async method that doesn't do anything. So let's just start with that one. And of course, I'll need using system later because I will likely do some console write lines and system.threading.tasks like this. Okay? So let me just compile this guy, async.cs. Let's not bother with, well, let's actually do an optimized build. Why not? Okay? So I have this. It complains about an async method lacking any await, and the whole thing will run synchronously. For demo purposes, we don't care. Okay? So let's just open this guy. And I could actually open it in ILSpy to make it a little bit more friendly. So we'll just go to C, demos, NDC, async.exe. Okay? And so here we go. I have my foo async, and it did a good job decompiling this thing. In fact, I got more keywords than I initially wrote, so that's also good. That's a bonus. I got a private keyword there. But I will actually go to View Options in ILSpy over here and just disable async method decompilation to take a look at what's going on. And now we start seeing something slightly more interesting. Now, how many of you have looked behind the scenes of async methods before? A few. OK, so this is a worthy endeavor to go through it. So what's going on here? I'm not going to go through all of the details. But effectively, what the compiler has done is built this beautiful little thing here called the async state machine. So the async state machine is the thing that's responsible to proceed your method when any of the things that are awaited inside the body finish. It's the thing that sort of does the bookkeeping. It's kind of, mimicking an instruction pointer. It knows where it is in the async method, and then if it needs to go to sleep because it hits an await for some operation that's not yet done, it will just say, I can return at a later point in time here, and it will go to that awaitable object and just say, please wake me up when you're done. Okay? And then it will re-enter, and the state machine will actually do a move next. Now, what you see here in the move next is that not much is happening because, well, there's almost nothing, in my method, but there's still some non-trivial stuff happening here. Well, first of all, we have an empty, try over here. Well, that's not very useful, but let's ignore that for now. And we also have this builder.setResult. That's the equivalent to me doing a return statement. Okay? Let me make this code a little bit bigger to sort of show you what this setResult thing is doing. So let me just go here and change that to task of int, and then over here do return 42. What we're going to see now is that this set result will actually correspond to this return 42. So when I recompile this thing, and I just hit F5 here in ILSpy, you see over here set result equals result, and result equals 42. Well, there's something interesting happening here already. Why didn't we do set result 42 here? We're doing set result after doing the result computation inside this try-catch block. That's because we want all exceptions that are happening during the execution of the async method to come out on the task and not escape somewhere on the thread pool. So if I make it a little bit more interesting once more, and I put in something to divide by, and I do 1 divide by d, I could pass in 0 and end up with a division by 0 exception. We want that thing to come out on the task and not on the thread pool somewhere in case we're beyond a certain asynchronous execution point. So if I go here, now it will become clear what that try-catch is for. That try-catch is sitting there to protect against anything that may throw exceptions. So pretty much all the user code will be in the try block. That we've already established. Everything inside the catch here is a way to signal the exception back to the caller through the task that was returned. And the set result at the bottom corresponds to a return statement. Okay? Now let's try to see whether if I introduce more return statements, I end up with more set result calls, right? So let me just do that as well. If d equals 0, then of course, from now on in mathematics, it shall be known that dividing by 0 returns 1983. Okay, beautiful. So we're redefining mathematics. Let's hit F5. Well, no, there's not more than one set result call. What's really happening here is that all my decision logic goes there, we store the result in a variable, we do all of this stuff beautifully inside the protected region, so in case something blows up, we don't blow up ourselves, and then we do set result at the end. Okay? So far, not super interesting because I'm not awaiting anything, like I'm just using an async method as an expensive way to return an integer by doing a heap allocation of a task, right? Not something you should be doing at home. So now let's actually change this to, first of all, let's actually keep it this way. And I'll just do await task.yield, which is the simplest thing I could be awaiting here. So what's going to happen now is that my method now needs to be split into two different stages. The first stage is the stuff that runs as soon as I call the method. And the second part that runs here is what happens after the task.yield eventually completes. So now the state machine starts having a purpose in life. It needs to track whenever it wakes up, am I before this task.yield or after this task.yield, okay? So now we'll see the method being split into pieces. So let me go here, compile this thing, and go back to that state machine. And then I'll also explain how the state machine gets kicked off at some later point, but now it starts to become interesting, right? So what you see here inside the try catch is the minimal thing required to effectively do this pause and resume of the async method. So let's just walk through it step by step. Well, first of all, we have our code setting here, task.yield in the middle. And this task.yield is interesting in the sense that it doesn't even return a task. It just returns a yield awaitable, which implements this whole awaiter pattern, meaning it has a getAwaiter. And the getAwaiter happens to have a result type, which is yieldAwaitable.yieldAwaiter. It's just an inner type inside this yieldAwaitable. So you see over here that there is some code that emitted getAwaiter on top of that. This is the code we had before. Compilers are allowed to do gotos, so don't worry about that. But over here, you see task.yield.getAwaiter. And now we can do two things. We can either check whether this thing is already done or whether it's not done yet. Let's assume that it's already done by the time you do the await. Everyone knows that if you try to do some asynchronous programming and you have a chance to do any kind of overlapping, you should do so, right? Like, this await doesn't have to be fused to a task. Like in the code I write in the Bing stack, for example, there's a lot of places where we do a whole bunch of tasks. Task T1 equals something, and then 7 hours later we do an await T1, right? So chances are that this T1 will already be done by the time we hit that await point, right? You don't have to do await ... everywhere. Like, you can store things in a local, and then by the time you await it, it may already be done, okay? So that's a very relevant case to actually optimize for, and this is this block over here. So this yieldAwaiter, if it's not complete, it will do something. Let's ignore that. But in case we're already done, we'll just fall through to not that point, but we'll fall through over here. So what's this thing? In case we're done, we'll do getResult, and that getResult may throw an exception because it's some asynchronous operation that has just finished, and then we do the rest of the method. Okay, so that's kind of what happens when this whole thing completes. Now, what happens in case this awaitable object says, I'm not done yet? That's the other case. That's what's happening here. So when we call getAwaiter, we check, are you done? And if it says, I'm not done yet, then we have to do the heavy lifting. And what's the heavy lifting? Well, the heavy lifting is we need to put ourselves asleep in such a way that we can be woken up as soon as that thing says you need to resume. So what are we going to do? Well, the first thing that we do is everything to do with this state thing. What you see here is this num, right, which is just a name that ILSpy has given this variable. In reality, it's not called num. In fact, it doesn't have any name in what the compiler emits. But so we read the state, which is kind of the instruction pointer of the state machine. And so the initial time, the state will be set to some value over here, and that causes us to enter this piece of code. And now we come to the conclusion that, starting in this state, we need to go to sleep because we just kicked off this asynchronous operation that's not done immediately. So we increment our state to the next state in the state machine. We say, when we want to be woken up, we want to be in state 0. What will that do? We'll re-enter this method at some point all the way from the top, and we'll jump to the else block, right? Because we have if num not equals 0, we'll do this, and if num equals 0, we'll end up over here. So we first set our state to the next state. And then we'll actually go through some levels of indirection, which I won't go into detail about, has to do with execution context and all that kind of stuff. We'll actually tell this awaiter over here, please attach this state machine to your body so that by the time you're done, you can actually kick him in the back and say, like, wake up, continue where you left off. So we're basically just telling the awaiter, here's the thing you have to wake up when you're done. That's what this indirection actually does, this await unsave on completed. Okay? Now there's something else happening here which is quite interesting. If you take a look at this whole state machine thing, notice this one keyword here, it's a struct. It's actually stack allocated. But of course, at the point that you need to do asynchronous work, this stack frame will return. What will happen? The task that comes out of the async method will be returned to the caller, where it may be awaited, and that may also return to the caller. So like, we're basically taking down our call stack. And if this thing is stack allocated, well, that memory is no longer valid. So what's happening is that this whole async state machine gets passed by reference to this helper method, this await unsave on completed, and that thing will actually box it to the heap. So in case you end up in the situation where your whole async method runs synchronously, no heap memory was killed in the process, okay? But as soon as you hit something async, you take the penalty of taking that whole state machine, moving it up to the heap so it can live longer than the current call stack, and then at a later point in time, we can resume it. So async methods start off cheap. Once you hit the asynchronous aspect of them, you pay some additional price, but that's a price that you're willing to pay because there's a lot of convenience in doing asynchronous programming this way, okay? So now, that's kind of the basics of how this works. Let me just make it more complex now by just adding a couple more things here. Let me do await task.yield and then do console write line 1 over here. And now I'm just going to copy paste this thing a couple of times, okay, like this, so that you get a chance to sort of see this state machine stuff in practice. So I now have 5 yields in here. I could do all sorts of loop constructs. Let's not bother you with all kinds of complex loop structures. But I just have 5 task.yields, and I could do other things here. It doesn't have to be task.yield. I could do task from result 1, I don't know, await another performance crime, task.run of nothing, whatever, right? Like you can be awaiting a whole bunch of things. Now, if I go back here and I compile this whole thing, and I go back to my state machine over here, well, now you start seeing what's really going on, right? Like my method has 5 stages of execution. In the past, it didn't look that complex because there were 2 stages and we compiled it using if-else. But now we have 5 stages of execution, so we need to have a big switch statement here. So if we're in state 0, we'll do this. If we're in state 1, we'll do this, and we'll jump to label F9. If we're in case 2, we'll do this. So for example, case 2, what's case 2 going to be? Well, case 2 is that thing with the task from result, apparently. So if I go here, once we're in case 2, we'll do the next thing, what needs to happen. So you see, in case 1, we need to do the from result. When the from result is done, we need to get the result of this task.from result and need to do the next thing. When this thing is done, we need to do another yield over here. I clicked on the wrong thing. But you sort of see all the parts of your method nicely split up into pieces. It's as if the compiler just took scissors and just cuts through all the await keywords and splits everything up, right? Okay, so let me just point out one more interesting complication of all of this voodoo business, right? Await is an expression. At some point, it was considered very early on in the design, should it be a statement or an expression? Well, it being an expression makes it very flexible because then it has a value and you can use it anywhere you expect a value, including in assignments. 99% of people will do int x equals await task.from result, but other people will do call a method passing in the result of awaiting something, right? So I can do something slightly more evil over here. So let me just get rid of all of this nonsense to write more nonsense. So what I will do is let me do console.writeLine of console.readLine. Okay. Let me actually try to outline this a little bit. I'm a little bit OCD, so it needs to be a little bit sexy. So console write line of console.readline plus, let me do another console.readline plus, and let me actually make this thing associative this way. Now it starts to look completely nonsense. But over here, await task.from result of hello. Doesn't mean anything. It will just ask the user to enter two things, right? Like, I will enter AB, and then it will print AB hello. Very useful, can likely make it a store app and charge 99 cents for it. We're not going to do that. That takes too much time. But so what's happening here is something quite interesting. What's happening is that before we're going to figure out that we have to go to sleep and wake up again, all of this nonsense with async state machines, we are merely executing stuff. We are executing a console read line, asking the user about something. Then we do another console.readline, and then ultimately we do this task from result, and we come to the conclusion, oh shit, we have to go to sleep. So how do you wake up all of this calculation that's already happening? What's happening here is that we have to store all of those intermediate results. So if I take a look over here, that's where you end up with this beautiful thing called a wrap. Okay? And this wrap is actually a feature called stack spilling. And that's the implication of having await as an expression. It can occur anything in a complex expression being evaluated. So normally what would happen if you have something like this is that the code that we would generate would be something like simply do console.readline, make a call to console.readline, make another call to console.readline, then load that string for hello or something, and then do some add instructions. Well, you can't do add instructions with strings. You have to call string.concat. But it would just be stack-based. You would just be pushing one thing on the stack, another thing on the stack, another thing on the stack, and then merely reducing the whole thing by doing operations like add and subtract and multiply and what have you. We can't do that anymore. We have stuff sitting on our evaluation stack, and now we have to go to sleep. Well, what you have to do at that point is evacuate the whole furniture, right? Write it all down on a piece of paper, put it somewhere on the heap, on a sticky note, so that when you wake up, you can restore it. And so those sticky notes are called wraps. So that's what's happening here, is normally those would just be sitting in local variables. But what happens is that we have to be prepared that at some point, this thing may have to go to sleep. So we better put it in a position when we have to go to sleep, we won't forget about it. So you see this console readline, they get assigned to wraps. And then later, over here, we are actually restoring all of this using those wraps that you see over here. So you see we're reading those things back from the fields at a later point in time. And that's something that you will see a lot for those more advanced language features, is that things that look like locals or that look like intermediate results may actually end up being fields on something allocated on the heap. It's actually exactly the same thing as with the closures that I was going to talk about for delegates and lambdas. Exactly the same thing. Something that looks like a local may end up somewhere sitting on the heap because it needs to live longer than you would normally expect. Okay? And then, of course, we also generate code to actually null out those wraps. That's a change that happened at some point because, well, if that async method runs for days and days and days, right, and you have some expensive object sitting there, it will, of course, be rooted and not be ready for garbage collection. So we need to also null out those fields as soon as we're done with them. In certain cases, if you have multiple await sites that have the same stack spilling requirements, it will actually reuse those wrap fields. So if there's other places where you need the same types, for temporary state to be stored, it will try to reuse those wrap fields as well. Okay, so that's what's going on with async methods. I'll just show you one more thing in the compiler source code. If you ever wondered how C# 6.0 did its magic to make it possible to await inside a catch and a finally block, let me actually make this bigger for the back over there. This file does everything needed to be able to do an await inside a catch block and an await inside a finally. It's not easy. There's a lot of stuff that needs to be taken care of. And so here you see like all those cases nicely documented. The C# compiler code is like a hit or miss in some sense. Some pieces are very dense and not really documented. Other pieces are heavily documented. So you just have to be lucky that day, and otherwise you just attach a debugger and try to figure out what's going on, of course. But so over here you see awaits containing finally blocks. There's a lot of stuff that actually has to be done, because what's really happening is that inside a finally block, there's a hidden hot potato. What do I mean with a hidden hot potato? There may be an exception sitting somewhere, but it's not even sitting in a variable, because it's the CLR, the runtime, that knows which exception is currently flying by, and that when the finally block is done, that exception needs to come out again to the caller, right? So it needs to sort of keep that state somewhere. Now, the C# compiler doesn't have an easy job here, because that exception is not grabbable inside a finally block. So if you do an await inside a finally, and we have to put that method to sleep, we sort of have to find that hidden potato buried in the ground, extract it, keep it somewhere, so we can rethrow it when that async method resumes. So all of this stuff happens here, and what's actually happening is if you have a try finally with an await inside a finally, you will not find any finally block in the generated IL code. It will become a try catch with a rethrow kind of thing. Now, the rethrow is not a plain rethrow. It actually says over here like throw EX, but in reality, it's not really using EX. It's using an interesting type, this guy, called exception dispatch info. How many of you know exception dispatch info? No? If not, you may want to know about it. Exception dispatch info is a type that was actually introduced in C#, well, not C#, in the .NET framework together with C# 5.0, is this little helper in system runtime exception services. And it's this thing that allows you to do a throw on an exception after you capture the exception. Now you will say, what's the big deal with all of this kind of stuff? Can't I just use the throw keyword to rethrow the exception? Well, if you rethrow an exception, the call stack gets reset, okay? So exception dispatch info allows you to pretend nothing happened. Like, you had an exception in your hand, and you want to pretend that you never saw it, never rethrew it. You will just rethrow it as if you never had anything to do with it. So what's really happening is that the C# compiler will generate code to rethrow the exception in the most innocent-looking way, so that you can't sort of even tell that it was ever there and touch the hot potato, okay? And again, this is something that happens over here if it's available. Like, if you actually compile this code before the .NET Framework version that doesn't have it available, then we'll just use a regular rethrow. So you can actually experiment with that, try to run this thing against different .NET Framework versions, and the call stack of an exception that's flying by through a try finally may look different depending on the .NET Framework version, because in some cases we don't have the utilities available to be able to pretend nothing happened. And so that's what we call over here the better rethrow, okay? So that's what's happening here. This file is a beautiful file to study if you want to see all the intricacies of how to deal with exceptions inside async and await, okay? Well, you don't have to deal with it, but like how the compiler deals with it, okay? So that's that one, and we just have time for a small dessert, okay? Well, I don't have to maximize this, you can read it. I only have 2 desserts today on the dessert card. One is about dynamic. That gives us a chance to potentially crack open WinDbg and do some native debugging if you're still hungry. Or we could do something really light, like a sorbet, which will be the transparent identifiers. Okay? Okay, the first one, dynamic. Yes, that's the chocolate lava cake. And transparent identifiers. Okay. I sort of influenced the poll over here, I think. Let's do dynamic, Transparent identifiers, there's a couple of very good blog posts about that one, actually, and I did that on a different talk. So if you go to the videos, you will likely find that one. So dynamic. People have a love-hate relationship with dynamic. I do as well. But, in cases where it's useful, it's useful. That sounds like a tautology. But here you go. I've just prepared a very simple piece of code here where I use static dynamic add, taking in 2 dynamics and doing A plus B. Okay? So this can just add two things together using dynamic, and those two things, can be anything that are addable, and it will figure it out at compile time how to do it. Now, why is this interesting? Because in some cases, and depends the kind of code you write, right? If you're dealing with dynamically typed objects and so on, well, this may be a good choice. But also, like sometimes in highly performance stacks, like the stuff I'm working on in Bing, sometimes we have to do a lot of late-bound stuff using reflection and so on. And then actually, you may want to consider, well, if we use dynamic, a lot of optimizations around reflection will be done for us without us having to do a lot of heavy stuff. Because once you start using dynamic, the code here that does A plus B will learn. It will become progressively better the more things you feed through it. And that all happens dynamically at runtime. The way that happens is by something called a polymorphic inline cache. Polymorphic inline cache. Okay? So what's going to happen is that the first time we call add with 1 and 2, this dynamic method will cry out to his daddy or mommy or whoever the compiler happens to be that day, and will just say like, help, I don't know how to add two integers together. And then the C# compiler will come in at runtime like a Superman and say, my son, here's how you add A and B together. Okay? You will cast them to int, you will do an add instruction in IL, and you will do a ret instruction. Okay? Go back to sleep, continue doing that. But then I will bother it with a second question, and so this polymorphic inline cache already knows, like if I get two ints, I know what to do, I don't have to bother the compiler anymore. But now I give it bar and foo. And now, oh my god, like how do I add two strings together? So again, it does the same thing. It checks, like, are those two things ints? No, they're not ints. Like, oh, they're things I don't know about. It will ask the compiler to give it a piece of code that it will compile. Using the JIT compiler, it will become as fast as if it's statically written code. And so it will now learn, well, to add two strings together, you need to cast the operands back to string, call the string.concat method, and there's your answer. And then the same thing for the datetime, and anything that may go through this polymorphic inline cache. So let me just show you this one, at runtime now. So I'll just run this with the optimizer turned on. So I'm just compiling this guy. It's called din for dynamic. Okay, and I'm just going to run din over here. Actually, let me run it with the debugger attached. How many of you have used WinDbg? Couple? Okay, yeah. So WinDbg is a native debugger which comes with the Windows SDK and a bunch of other SDKs, so you can definitely find it. It also tends to be forgetful about font settings. I swear that I actually changed it before I came down here. You either believe me or not, it doesn't matter. Here you go. So I've just started this. The right-hand side, don't bother with that, that's source code. So I'll just do G here to run this thing. So it's now running under the debugger, okay? And I'll just press enter. Well, let's not do press enter yet. Let me break into the debugger. So I will do debug.break. And now I will load something. Oh, by the way, I'm not supposed to show this, but this is, who knows Dave Cutler? He's the guy who built the Windows NT kernel. And I hit the breakpoint, I'm in his assembly code, so like, praise the Lord. So let me just close that. It's just an int3 instruction, so there's nothing secret about that one. But I'll just do load by SOS CLR to load something called Son of Strike. That's a debugger extension, native debugger extension for the CLR. And I can now do something like dump heap to dump everything on the heap. And I'll do it by type called dynamic method. That's something I happen to know, and there should be not much on the heap of that type, actually. I may actually get stuck here because it's trying to download symbols, and the Wi-Fi is not exactly fiber optic. But yeah, so like there's no objects on the heap of type dynamic method. So that's good. So let me resume this debugging session, and now press enter. This is where my code actually cried out to the compiler to say, help, I need to add two integers together, how do I do that? Okay, and so it now did that little dialogue with the C# compiler at the runtime, and it came to the conclusion that it now knows how to do that. And so you see it actually loaded system.dynamic, and all that kind of stuff. So I will now break this guy again, in the debugger, and I will, you can't get rid of Dave, he's 76, he still comes to work every day. So like he always pops up everywhere. But so here you see, we now have two dynamic methods sitting on the heap. And what I will do is I will take that one, which is 112 bytes long. I just happen to know that that's the one I'm looking for. You just poke around to all of these if you want to reproduce this. But you will do dump IL on those things and take a look at the IL code generated in that dynamic method. And what we see over here is actually code to unbox two arguments to ints. You see over here unbox to int32. All sorts of things to actually unbox those two guys. Let me also take a look at the other piece of generated code here. And you see over here, which one is this one? Here you actually see, oops, I've kind of lost myself here in the middle, but here it is. There you go. It has learned how to unbox two integers and run the add instruction to get the sum of two integers. It didn't know about it at compile time. At runtime, the compiler told it that's how you do it. So now let me actually resume this piece of code and bother that polymorphic inline cache by trying to add two strings together. So it's now adding two strings together. It again did that whole cry out for help thing to the C# compiler at runtime. And so when I break into this thing, and there he is again, I will do dump heap, and you see there's more methods that have been generated. So let me actually try to dump the IL code using dump IL for one of those new guys. And you see over here the C# compiler at runtime has told it to add two strings together. Please cast the two operands to system.string, then call system.string.concat on those two things, and there's your answer. So now when I call that thing again, it's as if that dynamic method was written by you at compile time to do type checks. If the two things are ints, I will do it this way. If the two things are strings, I will do it that way. You can't get much faster than that. So like even though dynamic may have a bad name for like doing a lot of heavy stuff at runtime, when you really need it, you can't really beat it all that much by doing your own kind of runtime code generation and all sorts of voodoo. Then it's actually a good thing to use. Of course, don't use it in a way that you do search and replace inside all your C# code and change all of var to dynamic, such that you have a JavaScript experience from now on. Some people have that as a fetish. I don't, but like you could do that. Don't do that, right? Like, but in cases where it's actually useful, it's actually darn useful. Okay. And of course, I could do G over here and actually let it learn about datetime offset as well. And it's actually terminating the process at this point, so I'm not sure whether I can still find it. But so if I poke in here, likely I will find out that it's now also learned about how to do the op_addition static method call to add a datetime and a time span together, because again, it cried out for help for that one. But now if I keep calling this thing with datetimes and time spans and strings and ints, it will be as fast as, static code almost. It needs to do some type checks, of course, but in a dynamic world without type checks, there's not much you can do. Okay, so that's kind of a whirlwind tour of a couple of language features. The key thing to actually take back home is this beautiful thing, right? Like a couple of years ago, the whole Roslyn effort started. It's now all available on GitHub and open source. Just Control F gets you a long way in finding things. Like if you hear, oh, they have this new thing called tuple deconstruction, and you know the word deconstruct and how to spell that one, you can do search all over here in the code base, and you will actually end up, finding a whole bunch of things that have to do with deconstruction. Take a look at the change list. Try to find like a coat hanger, like a little light in the darkness, like, oh, this looks interesting. That's this new language feature. Go to the commit list, and you will actually typically find the whole commit that has the whole language feature coming in as one big pull request into the source code. So a very, very nice thing to be able to dig into now. In the past, you had to sort of reverse engineer everything. Okay. So with that, I thank you for your attention and swinging by. I will be around, in the venue. So if you have any questions, please come to me. I will also be here tomorrow for a talk about .NET performance. I'll also have an Ask Me Anything with Bill Wagner over there tomorrow, I believe, somewhere around noon, early afternoon. Yeah, exactly. All right? Thank you.